Okay, so I'm going to talk about glassy pasta. If you find glass in your pasta, return it immediately. But in neutron stars, I'm going to argue we have reason to suspect that pasta is in an amorphous state, analogous to a glassy state. But before I get to that, I'm going to talk about something that was prompted by discussions yesterday that I did some hasty calculations last night. Apart from that, I have a lot of graduate and undergraduate students who have helped with various parts of this work. One of whom is sat in the corner at the back there. Zach was a summer student at A&M Commerce and is now here at the University of Washington. Okay, so I'm going to start with the other stories, which the stuff I did last night. So we heard a little bit about entrainment yesterday. There are, as we mentioned in the discussion, there are various ways of writing or parameterizing entrainment that Nicholas summarizes quite nicely in his paper from 2006. Basically what you do is you can write down this effective mass or entrainment matrix. What I've done here is I've expanded it in powers of proton fraction and kept first order because we're dealing with neutron star matter, so low proton fraction. Making sure that these still satisfy the sum rules that they have to obey. And this makes it explicit that the various parts of the matrix just depend on the neutron and proton microscopic effective masses. Here, these various things enter into this expression for the mutual friction coefficient and this entrainment parameter. So we have data on effective masses. There was some work that I was involved in a few years ago that extracted constraints on the isoscalar effective mass, the effective mass of nucleons in symmetric nuclear matter, and the effective mass splitting. Okay, how the effective masses of the neutrons and protons diverge as you increase the asymmetry, isospin asymmetry of the matter. So we analyzed a load of scattering data, came up with these constraints. We will argue that these are the best experimental extractions of direct experimental extractions of the effective masses. But they're not without flaws, but it's something to go on. And we can extrapolate these to high isospin asymmetry. If we just we need a model, so take the widely used Skirm model in which the effective masses of the protons and neutrons have this form, linear in density and isospin asymmetry, and you plug these constraints in, and you get a band for the entrainment parameter as a function of density. You get a band for the mutual friction parameter. I've also put here the numbers extracted from looking at glitch rise times. Bryn and I did this a few years ago. Last year, Vanessa Niels did it with the new better data from the 2016 glitch, and these are the ranges that we get. And notably, they are generally less than the extrapolated mutual friction.
Green does overlap?
Green overlaps all the way down to the bottom of red. Yeah, so these are consistent with each other. And the experimental data is at saturation density, and all of the densities are a model extrapolation, right? So that huge grain of salt. But even at saturation density, where we can probably trust this a little better the mutual friction parameter is higher. So that's interesting.
Well, is it?
I don't know.
Well, no, it's interesting, but
I mean, it is.
No, but let me just add.
Yeah.
I think you could add one thing to this picture, which is that you can't have too much superfluidity involved. So you
Right.
can't go too deep. So you could probably say,
Yeah.
you know, there's a cutoff at the density that if you take too much superfluidity, you
Right.
go too much inertia, right?
So the numbers you extract are sort of averaged value, and that may only involve a small part of the core or a smallish part of the core. Yeah. So.
But that maybe that's what the PF I'm thinking.
Right. So it may be
yeah.
down here is weighted much more. Yeah. Yeah. So it'd be interesting it'd be interesting to take this and average it over.
Because you could take this a set of gaps.
Yeah.
And ask how much? Yeah. That's cool.
Yeah. That'd be interesting. Yeah.
So entrainment in this case, it's present only when you have superfluidity or not.
Yeah.
So you need superfluidity to discuss the presence of this term, correct?
Yes.
Okay. Now you extracted some of the values from scattering data.
Yeah.
And typically those are relatively high energies. You see, we're carrying is completely irrelevant.
Yeah.
So how are you going to put those two together? You say that you need superfluidity to have entrainment, but at the same time you extract them from scattering where you don't need superfluidity at all. It's irrelevant. So how do you put these two things together?
So what we extract from the scattering data are the effective masses. So the question.
Yeah, but you have there, you see the coupling proton neutron too. You see,
yeah.
So that means you see that you need superfluidity. So how they come? And you need to explain how you extract it from some scattering, because it can be done in various ways.
Yeah, so this was within an optical model. Yeah.
I think you can probably explain scattering data without an effective mass.
Yeah.
Yeah. Okay.
Yeah, no, that's certainly true.
Yeah, but I think that's important to say.
Yes.
So putting that part aside, though, what you like, there's an entrainment term, you have to stay functional, but then you have to do a calculation.
No. There is something else here. See, the entrainment they discuss, it's only due to the presence of superfluidity.
No, that's what I'm saying. So there's the measuring of the masses gives whatever entrainment you put into your underlying functional, but then you have to calculate in the superfluid what's the effective entrainment, which might not be the same.
Right.
No,
yes.
Yeah.
So going from
I don't agree with you, but
Okay.
Superfluidity is only needed to have relative motions. That's it. The entrainment parameter.
No, you see what I'm saying is, in order to extract entrainment, you see something learn about that. Do you need the presence of superfluidity?
No, just relative motion between neutrons and protons. That's why we can extract.
Well, if you have normal fluids, you see, so then
you can extract from.
But then the only thing which you may have about motion is isovectors.
And that's why it's really.
Yeah, but there nobody talks about that. It's simply the interaction. You see, it's kind of the interaction.
Yeah, but pairing is not needed. Pairing is not needed. It's just relative motions between neutrons and
protons.
Well,
and of course,
maybe we should leave this for discussion. You see,
we'll bring it up again this afternoon.
Okay, that was my other story. Now I'll go on to the pasta. I'll talk a little bit about pasta. I'm gonna focus firstly on establishing as rigorously as possible how much pasta we should expect there to be. In other words, how much should we worry about it? And then secondly, what is it like? Right? If we have to worry about it, how hard will it be to worry about it? So just a reminder, the nuclear pasta refers to these non-spherical nuclear shapes that are predicted to appear at in the region between the crust and the core, the crust-core boundary, which is a very important region for a lot of the dynamics of the star. They may have a sizable bearing on observables. They arise because there's a competition between the bulk and surface energies of nuclei. There are many analogous systems on Earth in soft and dense matter systems. One of the best archetypes a solution of amphiphilic molecules, where you have a long hydrocarbon molecule which has a energetically disfavored interaction with water, and then there's some molecular head that has a relatively favorable interaction with water, and you start dissolving them in water. And as you increase the concentration, they spontaneously arrange themselves into spherical clumps and then cylinders, and then more complicated geometries and slabs. And we see all these types of this phenomenology in nuclear pasta as well. They're called nuclear pasta. There's a lot of effort that's been focused on trying to map out where in the nuclear matter phase diagram these phases lie. They're relevant. They exist at temperatures and proton fractions relevant for supernovae, protoneutron stars, and neutron stars in regions of density between 1/10 and 1 × 10⁻14 grams per cubic centimeter, and at temperatures up to about 10 MeV. What's the y-axis there? Sorry, this is the proton fraction. Right, so this is from about 30% protons down to 1%. Sorry. People model pasta in a lot of different ways. There are two microscopic modeling paradigms for pasta, if you like. And one of them is classical quantum molecular dynamics. Classical molecular dynamics is the most widely used of these two. Put neutrons and protons or particles in a box, which you evolve according to Newton's equations. You can put in some things that mimic quantum effects. The advantage of this method is you can simulate relatively large computational domains. The downside is that in general, in these simulations, you need large proton fractions for them to work, and you need to do them at finite temperature. So these simulations, they're good for simulating matter over here. There are no molecular dynamic simulations under neutron star crust conditions, which is important to emphasize. Okay. All of them have proton fractions of 10% or higher. But because of the large computational domains, we can, the relative speed of the method, you can do some interesting things. You can extract things like shear moduli from these simulations. The other microscopic way is to go full quantum, which can be done in density functional theory. So these are some simulations that we did a while back. So these are much more computationally expensive. You're solving several thousand coupled Schrödinger equations in a box. So you can typically analyze only much smaller computational domains. So you focus on one little strand of pasta. But again, you can, as density increases, you get all the phases of matter that you expect.
What do you mean by that?
So the simple periodic boundary conditions induce spurious shell effects because of the periodicity of the wave function. And the ways to get around that, but it involves significantly upping the computational cost.
So what is
so these are all different parameterizations of the Skirm density functional. The names themselves, so this one was fit to the APR equation of states, the microscopic calculations of Akmal, Panduri, and Ravenhall. They all means something to someone, but not a lot to most people. Yeah.
Quick question, can you do this in rotating quasi-periodic cells like we heard about yesterday? I don't know if anyone's even thought about that.
I don't know.
Have you thought about it? Okay.
The frequency of rotation is so
Probably
low.
Yeah,
it's not going to make any difference. Yeah.
It's irrelevant to the scale.
Okay, so you can do things like we've managed to map out the temperature phase diagram. And again, one thing I want to emphasize here is that this is starting out at a high proton fraction. This is the region in density temperature space occupied by the various Pasteur configurations. As you decrease the proton fraction, the melting temperature of Pasteur drops, and the region of density drops, until when you get down to proton fractions typical of the neutron star crust, in beta equilibrium, the phase diagram has shrunk quite a bit. And temperature, and Pasteur at these proton fractions tends to melt at around 1 to 2 MeV.
Well, can I ask?
Yeah.
So the Pasteur, how does that compare to the melting temperature of the lattice?
It's much higher. So 1 to 2 MeV is, so this is about an order of magnitude higher temperature than the
So the lattice
crust
will
melt.
melt first, but then,
Yeah.
okay.
Yes.
The crust.
The outer crust.
No, the inner crust, where this is in the inner crust.
Yeah.
So the crust will melt first, and then the Pasteur will.
Yes. Yeah. So Pasteur is. Yeah. I mean, Pasteur will, exist in the proto-neutron star, well before the crust is frozen out.
So there's a Pasteur, sorry, liquid Pasteur.
Yes. Yeah.
I shouldn't have gone there. I said, this was not.
Before you actually
I apologize for anyone.
could get in the process. This is why you're still kneading the dough.
Yeah, so overcooked Pasteur.
Yeah. Yeah.
Sorry, but still the temperature is the same for the white square than for the color one. So what? The temperature is the same on this calculation.
The melting temperature.
Spherical clusters, particularly spherical.
Yes. Oh, sorry. This is just a. This should be empty. Yeah. Yes. Sorry. Yeah. These should not be. Well, okay. Yeah. The gnocchi still exist, but they're not in a lattice.
So in fact, there are additional squares going back.
Yeah. Okay, let me, so these are just bits to the boundaries here.
But sorry,
yeah.
So if you take a proto-neutron star,
yeah,
right, and it cools,
mm-hmm.
the first thing that would form in these densities would be Pasteur, but not locked into a, all right, and then you freeze.
Yes.
A crust.
Yeah. So. Yeah. So. So if we go up here, so here this might be as the matter deleptonizes.
It's a race between the deleptonization
yeah.
and cooling. Oh, okay, so it's
yeah.
not. It's not. Okay.
Yeah. Okay, so I want to talk. So I put up some numbers here. The density boundaries of the Pasteur region, temperature boundaries. I want to try and quantify somewhat our uncertainty that comes from modeling. Like, see what are the extreme, how much Pasteur can we possibly make in realistic models? How little Pasteur can we have? And So there are two main sources of uncertainty. There's the modeling of the nuclear force and there's the modeling of the pasta. So the nuclear force is an ingredient of pasta. And the nuclear force is generally has a much larger uncertainty. Did anyone last week talk nuclear physics? How much do you think I should introduce? I want to take a little bit of care explaining the symmetry energy so everyone understands what that is. So, but taking a step back for a bit, yesterday we talked about how we need this hierarchy of models as we go to larger and larger scales. That hierarchy persists down to the level of quarks, right? Ultimately, the strong force arises because of interactions between quarks. So this is the chart of the nuclides on a log scale. And we have a great model for how quarks interact, but it is, unfortunately, neutron stars are in the non-perturbative regime. So we cannot directly calculate the properties of nuclei or nuclear matter from QCD. So we need to invent effective models of the nuclear force, which will have a bunch of parameters, and for the most part, those parameters are fit to subsets of nuclear data. And there is a huge amount of freedom to do that, and therefore there is a proliferation of models and parameterizations of models of the nuclear force. And this is a problem because although those models tend to work fine down here when you're describing nuclei, if we want to extrapolate to neutron star matter, we have to increase the proton and neutron number by about 50 odd orders of magnitude to get up here. And if we do that whilst maintaining the ratio of protons to neutrons you find in nuclei, then you end up here at symmetric nuclear matter. But we want to then extrapolate downwards to neutron star matter, which is much closer to pure neutron matter. Okay. So there's a extrapolation in density and isospin asymmetry, and our nuclear models diverge quite catastrophically when we do that extrapolation. Here is another way of depicting that extrapolation. Again, the phase diagram of temperature, density, and isospin asymmetry. Nuclear experiments give us data on what happens sort of around here, mostly confined to the density region around saturation density. And then we need to extrapolate up in density and out in isospin asymmetry. So there is a useful way to quantify this extrapolation and quantify the uncertainty that generates. You can write down the energy per nucleon for symmetric nuclear matter, for example, and pure neutron matter, so other way around, symmetric nuclear matter, which is this bottom curve here. Pure neutron matter is this top curve here. Symmetric nuclear matter is bound and has a minimum at saturation density where nuclei live. We can define the symmetry energy as the energy cost of turning protons into neutrons. And so, in other words, the energy cost of going up this way, of increasing the isospin asymmetry. Asymmetry energy would be a much better name for it, but symmetry energy is the one that we got stuck with. So the symmetry energy, in a simple way, can just be thought of as the difference in energy between this bottom curve and this top curve. Okay. Since most of our data comes from this density, then it also makes sense to expand the symmetry energy here in powers of density. And so we can write it as a magnitude, a slope, a curvature, and higher order parameters at saturation density, where this parameter here is just a convenient parameterization of our distance from saturation density. And this is particularly useful because these parameters can be directly related to neutron star properties at around saturation density. For example, the pressure inside a neutron star at saturation density is proportional to L, the slope of the symmetry energy, and has a higher order dependence on the magnitude of the symmetry energy there. So we can take all our models, calculate the symmetry energy, you get a whole mess of predictions for its behavior. Right? So we're kind of pouring all of our uncertainty into these parameters, and the goal is then to try and extract constraints on those parameters. Another way of getting up, this is a summary of experimental constraints on the slope of the symmetry energy and its magnitude from a variety of different experimental observables, nuclear masses, so just fitting models to binding energies of nuclei, neutron skins, which are one source of data that that probes matter that we think is closer to neutron star matter. So the neutron skin of a nucleus is simply the extension of neutrons beyond the protons in neutron-rich nuclei. And we can show that that is also proportional to the symmetry energy in the surface region of nuclei. But another source of constraints on the symmetry energy come from the theory side. We can calculate pure neutron matter using microscopic effective theories. In recent years, a new class of models has emerged, chiral effective field theory models, which are models that are models that obey the chiral symmetries of QCD. And sorry, my reorganization of slides, I've managed to lose a couple. Hold on a sec, let me see if I can find it. Oh yeah, okay. Okay, yeah, so you can perform calculations with these chiral effective field theoretic models. These models are quite nice because you essentially write down this chiral Hamiltonian and you expand it you can expand it, and there's a momentum cutoff built into it. And you can perform calculations at various orders. And the nice thing is that you know exactly how much error you're making at a particular order. And so you can quantify much more precisely the theoretical errors in your models. And you can typically, when you calculate the energy per nucleon of pure neutron matter, you get a band like this with fairly rigorously quantified errors. So what we have been doing is we've been taking the Skirm energy density functional and constructing models that are fit to the results of pure neutron matter calculations. And that spans systematically the uncertainty in the pure neutron matter equation of state that come from these models. And we take that as our starting point. We span the most conservative range of errors. And let me, okay. So this is a plot of the slope of the symmetry energy versus the curvature. And every triangle here represents one of our Skirm models. Right, so we populate this region here uniformly, and the shaded region here shows the region that is allowed by chiral effective field theory. Yes?
Question, comment. So in order to, like on the chart where you compare it with experiment, you have to make this so-called parabolic approximation where you got the delta to the fourth terms, right? If you want to connect what's measured in nuclei with what you've defined as the symmetry energy. Are you doing that in your Skirm functionals here have delta to the fourth terms? Okay.
Yeah. So the Skirm has the whole thing.
Okay.
Yeah.
So these are
so there's no parabolic approximation. Okay. Yeah. That's right. Okay. So this, as I said, the shaded region is the region allowed from chiral effective field theory. So we uniformly populate it. And then we can start calculating neutron star crust and core properties with these models. So here the color represents the crust core transition pressure, spanning a range from about 0.2 to 0.8, factor of 4 MeV per cubic Fermi. And based purely on the crust core transition pressure and the pasta transition pressure, we can calculate the thickness of the pasta relative to the thickness of the crust and its mass. This is a histogram of our models. This is the relative thickness of pasta. This is the relative mass of pasta. The models generally predict that the pasta layer is around 25%, a little bit above the thickness of the crust. The mass of the pasta is generally up around 60 to 65% the mass of the crust. So well over 50% of the mass of the crust is locked up in these pasta phases. The moment of inertia follows the mass pretty closely, so you can, the similar percentage moment of inertia of the crust is locked up in the pasta phases. Okay. No model predicts less than about 54%. I should mention that to calculate the pasta transition densities, we use a liquid drop model, a much simpler model to these microscopic calculations I showed earlier, because we can't run 487 model Skirms through that. But the liquid drop model has a surface energy that is parameterized, and we fit the parameters of the surface energy in that model to the results of our microscopic calculations in order to get as realistic a prediction for the crust core transition and pasta transitions. And when we compare the two, they are in good agreement.
Surface tension is pretty well defined.
Yeah. Yeah.
You don't have much freedom.
No.
So why do you say you have to fit it?
But in the liquid drop model, so in the liquid drop model, where you take your nuclei, you treat as a uniform density fluid, the external neutrons are uniform density fluid, and then you just write down some surface energy for the interface between the two. And that you have to extract from microscopic calculations. In the microscopic calculations, it's well, you know, there isn't any freedom there. You get
the thing which I don't understand from this trivial something. If I take a mass formula, better mass formula, I extract the surface tension from there, it's about 1 newton per square.
Yeah.
Which is pretty good.
Yes.
Right.
So that's
pretty much fixed, and all the terms should give you that. You say, no, you see, they'll be off.
Right. Yes, but
Spells actually are not much better than better formula.
No,
a little bit better, you see, but insensitively, so I would say.
So the problem here, though, is that these are super neutron-rich nuclei immersed in a bath of neutrons. The surfaces are much more diffuse. This is, you know, very, very different to the regime of isolated nuclei, which
so you mean by how much surface energy it's influenced by the presence of the neutron?
Yeah.
The effect of
you
neutron
get by that,
chemical
you get
potential.
some dependence. You see something which you understand somehow, because you can say, you see, surface tension is a function of the density of the is this. So how does it behave? Do you know, for example? I don't know. You see, neutron density is 0.
I think there are studies of the surface tension.
Yeah.
It's a function of outside neutrons, and it can drop like order of magnitude.
Yeah.
So surface tension goes to 0. You say?
Yes.
But then you all have clusters. I don't think that's correct. So it cannot be correct like that.
Well, it may be not to exactly 0.
Let's discuss this afternoon, because we have 2 talks this morning, so we can't run over.
Okay. Okay. So we can, if we want to calculate how the crust thickness and pasta thickness compares relative to the rest of the star, then we need to tack on a core equation of state. To span our lack of knowledge of the core equation of state, we use the well-used trick of adding polysopes at higher densities. So we extend our Skir models up to about 1.5 times saturation density, and then we add a couple of polysopes on. We tweak the polysopes. We're trying to parameterize our equations of state in terms of observables. So we tweak our polysopes to give specific values of moments of inertia and maximum masses. We can span we can reasonably span the range of uncertainty in the neutron star equation of state this way. And if we plot predictions of our models, so this is for the tidal polarizability versus the radius of a 1.4 solar mass neutron star. So this is with all of our models. So with the polysopes, we've now generated about 20,000 equations of state. So this is just their distribution in the polarizability radius plane. This allows us to examine the effects of both potential observational constraints and nuclear experimental constraints together. So for example, I've displayed here 3 more plots where we eliminate models based on various constraints that have been set by the by GW 1708-17. On the right here, so I should first say that the most powerful constraint in terms of the one that requires the least modeling is the extraction of a limits on the tidal polarizability of the neutron stars that merge from the gravitational waveform, from the in-spiral waveform, which sets upper limits to the polarizability of the binary system of around it depends. It depends a little bit on the analysis. It's around 600 to 800 or so is the upper limit. If you then perform a bit of modeling, numerical relativity modeling, and confront those models with post-merger observations, then you can set model-dependent bounds on the lower limit on the tidal polarizability of around 400. This is the from David Medici. This, I think, has been revised down to about 300. And you can also set limits on the maximum mass of a neutron star. So several papers found maximum masses of 2.2-ish. So both this limit and this lower bound here are very model dependent, but it's nevertheless interesting to see what effect those constraints have. This lower limit here is by far the most, the constraint that has the largest effect. So you can see that it cuts off models below a radius of about 11.5 kilometers here. Whereas the maximum mass constraints have little effect on the overall distribution of equations of state in this plane. So we can compare, we can calculate the thickness of the crust. So this is for all models. With this constraint here, we find that models are cut off below a crust thickness of about 800 meters. If you take the full range, the prediction for a 1.4 solar mass neutron star is that the crust thickness can be as low as 400 meters and as high as 1600 meters. So that is, this, I think, is a rigorous characterization of the uncertainty in the crust at the moment for a 1.4 solar mass neutron star. And it's a fairly sizable uncertainty, but observations have the potential to constrain it. You can, this is a plot of the crust thickness versus the neutron skin of lead. So we're now relating a neutron star property to a nuclear property. We can, so this is for all our models. This is for models that obey this constraint here. And you see this constraint in this case does not narrow down much the region in this space that is covered by our models. But the maximum mass constraint does chop off a lot of models below crust thickness of about 800 meters. I think these two figures are reversed. This should be up here. This should be down here. Yeah. So you can see here that a measurement of the neutron skin of lead isn't going to particularly constrain the absolute thickness of the crust. There's a fairly wide band at all values of the neutron skin thickness. But if you can then combine it with a constraint like this, you potentially get a much stronger constraint from a measurement of the neutron skin of lead. So combining astrophysical and nuclear observables, as we know, would be a powerful way to place constraints on neutron star properties.
But now this is where the parabolic approximation is important.
It is, but yeah. Again, we don't use, yes. So the parabolic approximation drastically, higher values of the symmetry drastically overestimates the cross-core transition density and pressure. So it is, yeah, it is important not to use the full equation of state. We can do a similar thing with the mass of the crust and the mass of pasta. I maybe won't go through all of these. I say I'm not going to go through all of them. I shouldn't go through all of them. Maybe I will, yeah, okay, here we go. So this is the relative moment of inertia of the crust compared to the star. Again, sorry, these numbers are a little small. So we're going from, this is for all our equations of state. This is versus the radius of the star. And we're going from about 0.01 up to about 0.09 for the relative moment of inertia fraction. If you neglect entrainment in the crust, then there's this classic constraint from the Weyl glitches that the relative moment of inertia must be at least 0.014, 0.016, depending. So it has to be above here. When you include entrainment, that can effectively increase that by a factor of about 5 up to around 0.08, in which case only a very small number of equations of state satisfy that constraint. This constraint here doesn't improve our information about the relative crustal moment of inertia. You've still got the same predicted range. We're just chopping off the smaller radius stars down here. But when you, this is the massive pasta, which again tracks the moment of inertia. This is versus the neutron skin radius. So again, while a measurement of the neutron skin radius isn't particularly constraining, if you measure a low value for the neutron skin, it does generally predict a low mass, but if you measure a high value for the neutron skin, there's quite a large range of masses for the, there's a wide range for the massive pasta in the crust. If you apply this constraint, then things become a little better. This correlation becomes a little tighter. I should mention this, the mass of the pasta here is in units of 10 to the 6 years times the Eddington accretion rate. So this, if a star is accreting at the Eddington accretion rate, then it would take between about 1 and 7 mega years to replace the pasta in the crust.
So
Yeah.
How accurately is neutron skin thickness was measured experimentally?
Not very at the moment. So the most direct extraction to date is from the PREX experiment from a few years ago, which set a range from, it set a lower limit, it was down around 0.1 Fermi, and an upper limit that was around 0.32, so up here, so somewhere between here and here. Right. Now, there are many other experiments that have extracted constraints that are much more model dependent in their analysis, right? And they typically predict ranges. You know, if I plotted them all, they would nicely cover the entire range. They're not constraining at the moment. Bottom line. Hopefully, now the PREX experiment, which is going to attempts to measure the neutron skin using a weak probe instead of an electromagnetic probe of the nucleus. That's going to run again, I think, this year. And so we should see tighter constraints soon.
We'll have to wrap up. So.
Okay, then let me very briefly talk about what pasta might be like. So when you do perform quantum simulations, what you find is that shell effects, both nuclear shell effects, or shell effects in the pasta, and of the unbound neutrons scattering off the pasta result in a large number of low-lying minima in the energy surface of the pasta. This was noted in the first 3D quantum calculations by Maciejewski and Heenan back in 2002.
Just a remark, I think
Yes.
there was also earlier paper by Aurel and myself.
Yes.
As well,
Yeah.
Semi-classical estimation of this.
Yes, yeah, so where you can analyze, you can, this is predicted in the, if you use the semi-classical model. So let me skip back to this. So, so we have tried to probe this more thoroughly. So we've been looking at the energy landscape of pasta as a function of the deformation of the nuclei. These are nuclear physicists' preferred parameterizations of the deformation of nuclei. This parameter beta just characterizes how much you are stretching or squashing pasta. Right? Higher beta, more stretch. And then there's this angle between 0 and 60 degrees gamma, which characterizes the sense of the deformation. So as you go from spherical, so spherical is with beta equal to 0. Then if you increase beta down here, you're producing more prolate deformations. If you go along here, you're getting more oblate deformations. So in pasta language, down here, you're making spaghetti-like structures, and over here, you're making lasagna. So we've been doing this and mapping, so this, the colors here indicate the energy per particle, and you see there are multiple low-lying minima separated by energy barriers of the order 10 keV per particle. And you can estimate a couple of things. You can estimate the temperature at which thermal fluctuations can jump you from one local minima to another. And you can estimate how these various local minima will be populated by different pasta structures. And given that temperature, you can also make an estimate of the long-range order of the pasta structures. This is an estimate of what length scale will thermal fluctuations destroy the straightness of spaghetti, for example. And you find that the length scale tends to be of order tens of lattice spacings, or 100 Fermi or so. So you can then ask yourself, well, what then, therefore, is the structure of matter as the star cools? Right? And I'll end on the next but one slide. I always wanted to reference the Journal of the American Ceramic Society. This looks an awful lot like what happens at the glass transition, where again you have multiple low-lying minima. The glass state tends to be characterized by a certain temperature called the fictive temperature in the language of glass people. And that is essentially the temperature I am estimating here. It's the temperature below which you would expect, classically at least, matter to get frozen into whatever local minima it ends up in. And you can characterize it with this temperature, and the minima are occupied with occupation probabilities just given by Boltzmann factors using this particular temperature. And microscopically, matter ends up arranged in domains. Okay, as you move around, you'll encounter some patches in this minimum, some in this minimum. So one possibility is that, let me end on this one. One possibility is that you might end up with microscopic domains of order tens of lattice spacings or hundreds of Fermi, each one inhabited by a different pasta or gnocchi shape, because these spherical nuclei, they still hang around in local minima even after pasta appears. So you may have a mixture of spherical and pasta at certain densities. So I will leave, I guess I'll leave it with that, leave you with that thought.
Any more quick questions?
This is at what density? This is supposed to be at a specific density.
This is at a specific density, yeah. So this, sorry, yeah, this is the energy. So this is the energy as you move around this surface. So this is just, I've taken trajectories as you move around here and just followed the energy here, so just so you can more clearly see the energy barriers and the relative positions and sizes of the minima.
So there are 3 different densities?
Yeah, sorry, the 3 different proton fractions. So this is one density, 3 different proton fractions around 0.02, but differing by up to 50%. So some of the, so there may be, as you go from one domain to another, you may also change the local proton fraction as well.
So what would happen to this picture if you also have superfluid neutrons and then you have interactions with vortices? Because those, the energies involved there are also kind
of order, yeah.
They can play that trick for you as well, rather than maybe.
Yes, they might.
Thought about that?
I have thought about it. I don't have an answer.
Yes,
yeah, but yeah, no. So what
is there an estimate for the size of this domain?
Yes. So the estimate from the size over which thermal fluctuations become important puts it at of order 100 Fermi, which is the size of a vortex. Well, so a vortex cores around 10 Fermi, right, on this scale, at this density.
Something like that.
Yeah.
But it puts it also at this scale. I mean, if I want to
so
look at the tension of the vortex.
Right.
Or maybe smaller.
Right. So the vortices will see the domains.
Yeah, so they go through different domains.
Yeah.
Okay. All right. Thank you very much.
Thank you.